Okay, on Friday, we finished up our conversation of iron oxidation kinetics by describing a four-step mechanism in which iron 2 initially reacted with oxygen to produce iron 3 and superoxide. Superoxide then went on as an intermediate to react with iron 2 to produce iron 3 and O2 2 minus, also known as hydrogen peroxide. Hydrogen peroxide is now a second intermediate. It will react with iron 2 to form iron 3 and 2 species, the hydroxide ion, and importantly, the hydroxyl radical, which is our third intermediate species, which now completes our four-step series of oxidation reactions. And the hydroxyl radical reacts with iron 2 to form iron 3 and a second hydroxide. And that is how we can have pseudo first order kinetics for iron 2, as long as we have lots of excess oxygen, or second order kinetics of iron 2 and oxygen if both are about the same concentration, and still have a stoichiometry of iron to oxygen of 4:1. And it's because these intermediate species, superoxide, hydrogen peroxide, and hydroxyl radical, all react very quickly with iron in solution. So again, this is an example of reconciling a mechanism with a series of elementary reactions. The last thing I want to say while I have this slide up is to recognize that the observed kinetics of iron oxidation rely on K1, the first rate, being slower than K2, K3, or K4. In other words, we say that the first step is rate limiting. So what I want to do now is actually implement these reactions into a Excel spreadsheet where I can actually calculate the concentration of iron 2 versus time, the concentrations of all the intermediates versus time, to make the point that the intermediates are formed early on in the reaction process, reach a steady state concentration, and then persist over the course of the reaction. So I will close this and open up my spreadsheet. So in order to build a real spreadsheet for iron oxidation, I actually have to know the rate constants. And so this table, which is based on a paper we wrote, 25 years ago, lists the key series of reactions that you might consider for iron oxidation. Iron 2 reacting with oxygen, that's reaction 1 that we just talked about. There's a pH dependence to this reaction, and in this older paper, this is a bit of a crude but useful formulation which allows us to calculate the K as a function of pH. I have a second reaction for superoxide. Then I have the reaction for hydrogen peroxide. Again, a crude pH dependence here. If you ever need to, we can do a better job at explaining that pH dependence now. And then finally, the iron reaction with the hydroxyl radical. I will point out that iron 3 can react with superoxide to give us iron 2 and oxygen. That actually has a pretty fast rate. I'm going to ignore that reaction for today's treatment, but this is common that the sort of mechanisms that we describe in sort of an academic context are often a little bit simplified, and that's often, and in this case, is certainly true. So now that I have these reaction rates, I can go up into my spreadsheet, and let's see how I implemented this. So click 7.6, that's going to be the pH to get started. These are going to be my three reactions, 1, 2, 3, and 4. You notice I listed the species in column B. I list the rate constant in column C, and the units here are reciprocal molar, reciprocal seconds. So you'll notice that reaction 1, and these are all bimolecular rates. So the first one's iron times oxygen times the rate constant, and that's on the order of 27. Let's see. The next one's on the order of 1 times 10 to the 7. So when we say the first one's a lot smaller, boy, it is. The next one's almost on the order of 10,000. Okay, so again, pretty big compared to 27. And the last rate is 5 times 10 to the 8. It's close, if not at, diffusion control rates. So our assumption is valid. K1 is much, much smaller than K2, K3, and K4. Now, to start the problem, I've got to establish some boundary conditions. And a boundary condition is just the conditions at the beginning of the problem, the boundary. And so I will use 100 nanomoles of iron 2. And that's on the high end of what we would see in the environment. But that's what I picked, 100 nanomolar. I also needed to put in the oxygen concentration. And we know from our solubility of oxygen work that it's going to be around 300 micromolar, somewhere between 200 and 400 based on temperature and ionic strength. And it's in micromolar, not nanomolar, so I'm going to need to make the appropriate conversions. So how do I set this up? Well, I set it up by starting at time 0, so there's time in column B right here. And then I'm going to have concentrations. So iron at time 0 is 100 nanomolar, or 1 times 10 to the minus 7 molar. Oxygen is 3 times 10 to the minus 4 molar. And all of my other species have 0 concentrations. The boundary condition, if you will, is that before you start the reaction, they all have they don't exist. So that's my conditions right there. Okay, the next thing I need to do is to calculate the rate of change. So what I have done is I have calculated the rates for reaction R1, that would be this one, reaction R2, reaction R3, and reaction R4. So let's take a look at R1 to see what's involved. Okay, so the rate, again, this is a bimolecular reaction, is C$4, which is the rate constant, C15, which is the iron concentration, D15, which is the oxygen concentration, and those three terms would describe the rate of change of iron with respect to time. But I'm doing this over a short period of time. I'm not doing this per second. I'm doing it over 100th of a second. And that's to make sure that my small time step is not... I'm using small time steps in this kinetic model, small delta t's, so that I don't have bad things happening to my model. If I step too far into the future, I can generate negative concentrations when things are exponentially decaying. All right, so this is delta iron, this is really a column of delta iron because I'm calculating delta iron over delta time is equal to the rate constant times iron times oxygen, and I've multiplied this by my delta time. Notice the trick, I made my time steps constant all the way down, so I just picked up my first time step in cell B16, and so I'm going to use that as my delta T in all of my rates. All right, let's go look at R2. Well, R2 is nothing more than K2, iron. Now it's superoxide concentration, which is 0, okay, and delta T. So notice that R2 has a value of 0 in the first row. R3, K3, iron, hydrogen peroxide concentration, delta T, and again, it's also 0 in the first row. And then finally, R4, which is C7, which is K4, iron, hydroxyl radical concentration, and delta T. So that takes care of my first row. Well, what's my second row? Well, my second row is simply the first row. It's the iron concentration I had a hundredth of a second before, plus the rates in row 0. So I subtract the rate in I15, J15, K15, L15. So the column C is my iron concentration. And since these rates are the disappearance of iron, I subtract all 4 of them off of that cell. Now, that's pretty simple in the first step. It's just simply R1 because R2, R3, R4 are all 0 in the first row. Well, what about oxygen concentration? It turns out I use up a little teeny bit of oxygen by oxidizing iron, and so now I have D15. D15 is the oxygen concentration, minus R1, because R1 is the rate of consumption of iron, and it's also the rate of the consumption of oxygen. Now take a look at column D all the way down. You can see to 3 sig figs, that number doesn't change very much. Oxygen is in significant excess, and so that species changes very little over the course of the reaction. Well, let's go to superoxide. Superoxide now is it's a little more complicated. It's going to be the initial concentration, which is E15, plus the amount we get from the first step. So remember, the first step consumes oxygen and produces superoxide. So reaction 1 increases or rate 1 increases the superoxide concentration, and rate 2 decreases the superoxide concentration. So that gives me now an estimate for superoxide. How about peroxide? Well, it's the initial peroxide concentration plus the amount I formed through reaction 2 minus the amount that I lose through reaction 3. And finally, the hydroxyl radical, again, amount I start with, plus the amount I add from the reaction of hydrogen peroxide with iron, minus the amount, which is R4. So I am now done. And finally, iron 3. Well, iron 3, what is this number? I have no idea what this number is. This is craziness in this spreadsheet. I actually calculated iron 3 out here, and iron 3 in this case is simply the iron 2 concentration I started with. So there's $C$9. $C$9, that's the iron 3, minus C16. And C16 is the iron 2 concentration that's left behind. So if you start with 100 nanomoles of iron and you got 99 nanomoles left, you got 1 nanomole of iron 3. So that just comes from a simple mass balance. And then finally, it's interesting to plot at any given step the loss of iron to the loss of oxygen. And you notice this is 1. And that's because when you start this reaction, R1 is the only rate. 2, 3, and 4 are all 0 because there is no superoxide, there is no hydrogen peroxide, there is no hydroxyl radical. So the stoichiometry of iron 3 produced to oxygen is 1, and you can go ahead and you can follow this down over the course of the reaction. Let's go see if it's the sum of all of the rates. So that's the sum of the loss of iron 2 to the rate R1. So again, it's the loss of iron to all of the mechanism to the loss of iron due to the first or the oxygen-based reaction. And I've got a typo here, so let's fix that. There we go. Iron 2 to oxygen. So we said that the observed stoichiometry is 4:1. It is, but only when you have a significant concentration of iron in your system, and that significant concentration has a chance to oxidize and reach steady state. Okay, so now I've described how I got to sell B16, and you'll notice B17 and B18, they look the same. So what they're doing is again taking the iron concentration and subtracting off all R1, R2, R3, R4. What's changing out here is these cells actually have real values because these concentrations have real values. And so you'll notice they're quite small. 3 times 10 to the minus 18 is really small, but they're real. And so we're going to carry them all the way down. And because I had to use a small time step, I had to go a long way down to get out for 60 seconds, a minute run. I had to go out to row 6,000, right? So I have simulated this with 6,000 unique time steps. So let's look at the result of my model. So here in this plot is my result. Time on the x-axis is in seconds. Iron 2 or iron 3 is plotted on the left axis. Blue is the iron 2 concentration. It starts at 100 nanomolar, 1 times 10 to the minus 7 molar. Notice my units are molar. It starts at 100 nanomolar at time 0, and it decreases down to about 30 nanomolar at time 60 seconds. You can start to see the clear exponential decay in that blue line. The iron 3 concentration is just the opposite. It's the yellow line. As iron 2 goes away, iron 3 goes in. Again, you can see that exponential curve. Now let's go look at the intermediates, and the intermediates that we'll want to pay attention to are the superoxide concentration. Notice superoxide starts at 0, and then as you start doing reaction 1, you're making superoxide, so it goes screaming up, and then at about 5 seconds into the reaction, so 50 steps in my sequence, the superoxide concentration reaches steady state, and the steady state concentration it reaches is 8 times 10 to the minus 10, or 0.8 nanomolar. So not a lot of superoxide in there because it is much more reactive, so you don't need as much to give you the same rate. So what's ends up happening is you see these rates right here, 8 times 10 to the 12, 5 times 10 to the 13. Well, let's scroll down. What did we say? It reaches steady state at about 10 seconds. So let's go down to 10 seconds. That's good enough. 6.9 times 10 to the 12. 6.93 times 10 to the 12. That's what we mean by steady state. The rate at which it's produced is equal to the rate at which it leaves. And when those two things are equal, you have a constant concentration. So the orange line here is the superoxide concentration. And the gray line is the hydrogen peroxide concentration. And it hasn't quite reached steady state in 60 seconds. It's getting there. All right, so that's the implementation. It's a simple finite difference implementation for a complex kinetic mechanism. And I started by saying that I was doing this at pH 7.6. The oxidation rate, reaction 1, goes faster at higher pH. So let's go ahead and change that from 7.6 to 7.8. And now let's follow that blue curve. Notice my blue curve now goes down much more steeply. My iron 3 is almost up to 100% or 100 nanomolar. Increase the pH in this range and you get a very distinct increase in the rate. So there's my iron 2. And now you notice the superoxide still looks the same. It's still coming in at around 2 times 10 to the minus 9. So actually higher concentration of superoxide because I increased R1 but left R2 the same. So 2 nanomolar. And then look at my hydrogen peroxide. The hydrogen peroxide is now just about at steady state. I had to go out to 60 seconds. Okay, the last thing I want to show you is why this time step is important. So I'll try to increase the time step to 0.05. And when I do that, you can see my spreadsheet here gets pretty ugly pretty fast. And what's happening is I'm getting negative numbers in my rates. Why am I getting negative numbers in my rates? Let's see if I can go find these. Where are they? Right in here. I'm getting negative numbers right in here in column L. And what's happening is I'm overshooting. I'm actually subtracting too much off of the hydroxyl radical concentration. In other words, in 0.05 seconds, I violate the condition that the reaction rate is linear over that small range. So I'm going to go back to 0.01, rebuild my spreadsheet, and I built this spreadsheet by playing around with that time step so that over that time we can assume that the reaction is effectively linear, not exponential. And that time step has to be really short for reactions that are really big. Okay, so 4 reactions, all simulated correctly by calculating their concentrations, their rates of change, and stepping my way through. And you can clearly see the production of intermediates in this example.